Hello and welcome to Controllers Tech. In the previous video, we saw how to use queues in FreeRTOS to transmit data between tasks, that is, for inter-task communication. Queues are well suited for transferring data, but sometimes tasks simply need to coordinate with one another. For example, if one task is using a peripheral, the other task must wait, otherwise, the data being transferred to that peripheral will get corrupted. Even a high-priority task must wait before it can access a shared peripheral. This coordination is the job of semaphores and mutexes. In this tutorial, we will see how to use semaphores in FreeRTOS. We will cover both types, binary semaphores and counting semaphores. We will also look at the advantages of using semaphores, the drawbacks of binary semaphores specifically, and how mutexes overcome those drawbacks. Before we start the project, let's go over what a semaphore is, and how it works. There are two types of semaphores in FreeRTOS. The first is a binary semaphore, which has only one token. It can be either 0 or 1. When a task takes the semaphore, the count drops to 0. When the task releases the semaphore, the count rises back to 1. To understand why this is useful, consider the following scenario. Suppose we have two tasks, one of high priority and one of low priority. Both tasks want to use the UART peripheral to send data. Now imagine that the low priority task is in the middle of sending data when the high priority task preempts it, and also begins sending data. At that point, the data in the UART peripheral will get corrupted because two tasks are writing to it simultaneously. To prevent this, we can use a binary semaphore to block access to the shared resource, that is UART in our case. Here is how it works. The low priority task first takes the semaphore, then begins sending its data. The high priority task preempts it, and also tries to take the semaphore. However, since the semaphore is already taken by the low priority task, the high priority task has no choice but to wait. Once the low priority task finishes its UART transmission and releases the semaphore, the high priority task can immediately acquire it and begin transmitting. This way, we effectively place a semaphore wall around the shared resource, ensuring that only one task can access it at a time. The second type is the counting semaphore. Here, instead of just one token, it has multiple tokens. For example, if we have 3 shared resources, we can create a counting semaphore with a total count of 3. Now suppose we have 5 tasks competing for those 3 resources. Since there are only 3 tokens available, only 3 tasks can acquire the semaphore and access the resources. The remaining 2 tasks have no choice but to wait, regardless of their priority. If a task does not hold the semaphore, it cannot access the resource. We will see this in practice in this video. Now that we understand what the binary and counting semaphores are, let's implement them in the project. Let's start by opening Cube IDE. The project from the previous video, Part 3, is already loaded. Let us first rename it to Part 4. While renaming, make sure the Update References box is checked so that the name change is applied at all relevant locations. Alright, the renaming has been done. Now delete the debug configuration from the previous project, and rename the IOC file to Part 4 as well. Next, open CubeMX and load the Part 4 project. This is essentially the Part 3 project with just the name changed. Go to FreeRTOS Tasks and Queues. Here you can see the tasks from the previous project. We need 3 tasks, but we are going to rename them. Let's modify task 1 first. We will name it LPT, which stands for low priority task, and set its priority to below normal. Make sure the stack size is large enough, since we will be using printf to print logs to the serial console. Also update the entry function name to match. Now let's modify task 2, We will name it MPT, which stands for Medium Priority Task, and set its priority to Normal, which is higher than LPT. The stack size should again be 512 words, since we will also use printf in this task. Finally, task 3 will be the high priority task, so its priority should be set to above normal, making it higher than both of the other tasks. Our 3 tasks are now ready. Let's also delete the queue from the previous project since we no longer need it. Now go to Timers and Semaphores. Here you can see separate sections for creating binary semaphores and counting semaphores. We will start with the binary semaphore. Keep the name as my binary sem01. The initial state determines whether the semaphore starts as available or depleted. As mentioned earlier, a binary semaphore has a maximum count of 1, so it is either available or it is not. If we set the initial state to available, the first task that tries to take it will succeed immediately. If we set it to depleted, the semaphore must be released by some task before any other task can acquire it. We will set it to available so tasks can acquire it without any issues. Keep the allocation set to dynamic so the semaphore takes its memory from the FreeRTOS heap. Now if you look at the FreeRTOS heap usage, you will see an error because we have exceeded the configured heap size. Go back to the parameter settings and increase the heap size to around 10 kilobytes. The error should now be gone. The UART is already configured from the previous project, which we will use to route printf output to the serial console. That is all the configuration we need. Let's click Generate Code to generate the project. Alright, let's open the Cube IDE again. You can see the project has been updated with the new tasks. Let's first take a look at the main function. Here you can see the semaphore has been created using the function OS Semaphore new. Its max count is 1 and its initial count is also 1. The max count is always 1 for a binary semaphore, and the initial count is 1 because we set it to available in CubeMX. So by default, the semaphore is available for any task to take. We have our 3 tasks, LPT, MPT, and HPT. Now let's scroll down and write the task functions. Let's start with LPT. Here I am going to define a wait variable, which will be controlled inside the infinite loop. The task will first print an entry log to the serial console, then call OS Semaphore acquire to acquire the semaphore. Since the semaphore is already available, it can be taken immediately. The first parameter of this function is the handle of the binary semaphore. The second parameter is the timeout, and this is important. It determines how long the function will wait for the semaphore to become available before exiting. If we set it to 0 and the semaphore is not available, the function will immediately return with an error. On the other hand, if we set it to OS wait forever, the function will block the task indefinitely until the semaphore becomes available. This is how it should actually be used. Since we want to block access to the shared resource, we must wait forever. So the task waits until it can safely acquire the semaphore. Once the semaphore is acquired, the task will print another log, and then simulate resource usage by decrementing the wait variable inside an empty loop, until it reaches 0. During this time the task is actively running, simulating a resource being used by LPT. Once the wait variable reaches 0, the loop exits and the task prints a log, indicating it has finished accessing the resource. Finally, it releases the semaphore using OS Semaphore release, after which the task goes to sleep so other tasks can run. Now let's write MPT, the medium priority task. The structure here is largely the same. It first prints an entry log, then tries to acquire the semaphore with OS wait forever. Once acquired, MPT simply prints a completion log and releases the semaphore. It is not simulating any resource usage or waiting inside a loop, it just needs the semaphore in order to print the completion message. So what we want to observe here is this: if LPT has acquired the semaphore, and is busy inside the wait loop simulating resource access, can MPT, which has higher priority, is able to preempt LPT, and print its completion message. That is what we are going to find out. We also have the high priority task, HPT, which we will not use for resource access in this example. We will simply print one log from it so we know it ran. This task does not need the semaphore at all, so it will not block, it will simply run and continue. This is an important point to understand. Even though LPT holds the semaphore, it does not block the RTOS scheduler entirely. The semaphore only blocks tasks that actually try to acquire it. A task that does not need the semaphore can run freely, regardless of who holds it. HPT is a perfect example of this. It has the highest priority and does not need the semaphore, so it will always run without any interference. Let's build the project and flash it to the board, so we can observe the output on the console. I will be using the Arduino IDE serial monitor for the output, because it has a timestamp feature, which will help us understand the exact sequence of events and their timing. Let me reset the board once so we can observe the output from the beginning. Alright, let's go through what is happening here. Everything starts with HPT running first, which is expected since it has the highest priority. Once it goes to sleep, MPT runs. Since the semaphore is available by default, MPT acquires it, completes its operation, and releases it. After that, LPT runs, acquires the semaphore that was just released by MPT, and begins simulating resource usage by entering the empty while loop, which runs for around 5 seconds. Now, MPT has a delay of only 200 milliseconds, so it wakes up again well before LPT finishes. It tries to acquire the semaphore, but since LPT is still holding it, MPT is forced into a blocked state, waiting for the semaphore to be released. Meanwhile, looking at the timestamps, you can see HPT continues to run every 1 second because it does not need the semaphore, and is completely unaffected by who holds it. After around 5 seconds, LPT finishes its loop, releases the semaphore, and as soon as that happens, MPT acquires it, completes its operation, and releases it again. So this demonstrates exactly how a binary semaphore works. After LPT acquires the semaphore and begins accessing the shared resource, MPT cannot preempt it to access that same resource, despite having higher priority. LPT, despite being the lowest priority task, can safely hold off a higher priority task from accessing the shared resource, for as long as it needs to. At the same time, HPT runs freely throughout because it never needed the semaphore to begin with. This is the core behavior of a binary semaphore. It ensures that only one task can access a shared resource at a time, and task priority alone is not enough to bypass that protection. Now let's see what happens when we modify the task behavior a little. Inside LPT, I am going to reduce the wait time so the empty loop now runs for around 1 second. The value of 1 million corresponds to approximately 1 second on this development board at its current clock speed. The rest of the function remains the same as before. Inside MPT, we will also implement a wait cycle, but this time MPT will not acquire the semaphore at all, it will simply run the empty while loop for around 5 seconds on its own. Since MPT does not need the semaphore, it can run freely even when LPT is holding it. HPT, on the other hand, will now be the task that needs the semaphore. It will acquire it, print some logs, and release it. Let's build and flash the project to the board. Let me reset it so we can observe the output from the beginning. Alright, so here we can see HPT runs first, which is expected. The semaphore was available by default, so HPT acquires it, runs its task, and releases it. After HPT goes to sleep, MPT starts running its empty while loop for around 5 seconds. During this time, HPT wakes up periodically, it preempts MPT, acquires the semaphore, runs its task, and releases it. This keeps repeating. Now, notice that LPT does not appear in the logs at all during this period. The reason is that MPT is running its empty while loop and has not entered a blocking state, so the scheduler never gets a chance to run LPT. HPT can still run because it has higher priority than MPT and can preempt it, but LPT simply cannot get any CPU time until MPT finishes. Once MPT finishes its loop, LPT finally gets to run. It acquires the semaphore, which is available at this point, and begins running its own empty while loop for 1 second. During that time, HPT wakes up and tries to acquire the semaphore, but since LPT is holding it, HPT is forced into a blocked state. Now MPT also wakes up and starts running its loop again. Since MPT does not need the semaphore, it preempts LPT. Now we have a situation where LPT is preempted by MPT and therefore it cannot finish its loop. Also the HPT is blocked waiting for the semaphore, and MPT is running freely without holding any semaphore at all. Technically, LPT should have released the semaphore after 1 second, which would have unblocked HPT. But because MPT preempted LPT before that could happen, LPT cannot run, cannot release the semaphore, and therefore HPT remains blocked, waiting on a medium priority task that is not even holding the semaphore. This is exactly what is called priority inversion. A medium priority task is effectively making a high priority task wait, not because it holds any resource the high priority task needs, but simply because it is occupying the CPU and blocking the task that does hold the resource. This is one of the most significant issues when using binary semaphores in FreeRTOS. Priority inversion can be solved by using a mutex instead of a binary semaphore. A mutex supports a feature called priority inheritance, where the priority of the task currently holding the mutex is temporarily raised to match the priority of the highest priority task waiting for it. This prevents lower or medium priority tasks from starving a high priority task that is waiting. We will cover mutexes and priority inheritance in detail in the next tutorial. For now, I hope the behavior of the binary semaphore is clear. We will now move on to counting semaphores, which allow us to protect access to multiple resources simultaneously by using more than one token. Let's go back to CubeMX to configure the counting semaphore. Inside CubeMX, I am going to add one more task called VHPT, which stands for Very High Priority Task. Its priority is higher than all the other tasks we have created so far. Now go to the Timers and Semaphores tab, and we will create a new counting semaphore. I am setting the max count to 3, meaning there can be a total of 3 tokens inside it, and the initial count is also 3, meaning all 3 tokens are available by default. Now remember, we have 4 tasks but only 3 tokens, so we will see how these 4 tasks compete for 3 resources using these tokens. Our goal is to ensure that no 2 tasks can access the same resource at the same time. Let's generate the project and go back to Cube IDE. I am going to make some changes to the code. Here I have a resource array which holds 3 resources, and all 4 tasks will compete to access them. There is also a character array that tracks resource ownership, indicating which resource is currently held by which task. The function getResource will be called by a task to gain access to a resource, and similarly releaseResource will be called to release it. The function printResourceTable will print the current state of all resources, showing which task holds which resource at any given point in time. Now I am going to make changes inside all 4 task functions. Let's start with LPT first. Define a resource ID variable. Then inside the infinite loop, the task will first print an entry log and then try to acquire the counting semaphore. After acquiring the semaphore, it calls getResource to claim one of the available resources, prints a log, and then calls printResourceTable, so we can see the current ownership of all resources. It then enters a blocking state for 2 seconds, simulating active use of the resource. Finally, it calls release resource to free the resource, and then releases the semaphore token as well. Now let's do the same for MPT. The structure is exactly the same: define the resource ID, acquire the semaphore, get the resource, print the log and resource table, block for 2 seconds, then release the resource and the semaphore. The only difference is the task name. We will follow the same pattern for HPT and VHPT as well. All 4 tasks behave identically in terms of flow, the only thing that differs is the task name. What we want to verify is that no 2 tasks ever hold the same resource at the same time. Let's build the project and flash it to the board. We do not need the Arduino IDE for this, let's just use a regular serial console. Let me run this for a while so we can observe the output. It started with VHPT running first, which is expected since it has the highest priority. It acquired the semaphore, accessed the first resource, 111. The resource table shows that the resource 1 is held by VHPT, while the other 2 are free. After acquiring the resource, VHPT enters a blocking state for around 2 seconds. Within that time, HPT runs, acquires the semaphore, and accesses the next available resource, 222. The resource table reflects this. After HPT goes into the blocking state, MPT runs and acquires resource 3, and again the resource table confirms this. Now all 3 tokens are held by VHPT, HPT, and MPT respectively. At this point, LPT runs and tries to acquire the semaphore, but all 3 tokens are already taken. So LPT has no choice but to wait. While LPT is waiting, VHPT finishes its blocking period, releases the resource and the semaphore token. It then immediately preempts the LPT to start its next cycle. This keeps happening, but at some point you can see LPT also gets access to a resource. The access to the 3 resources keeps cycling among all 4 tasks. It is not limited to the 3 higher priority tasks. Every task gets access eventually, but only one task can hold 1 resource at any given time, which is exactly what we wanted to achieve. You can think of these resources as 3 instances of a UART, 3 ADCs, or any combination of peripherals. Generally, peripherals are the kind of shared resources that produce errors when accessed by multiple tasks simultaneously, so using counting semaphores or binary semaphores is the right approach to protect them. So we have seen how both binary and counting semaphores work in FreeRTOS. We saw how to protect multiple shared resources by creating a counting semaphore with the same number of tokens as resources. We also saw the issue of priority inversion with binary semaphores, where a medium priority task blocked a high priority task from running, not by holding the semaphore itself, but simply by occupying the CPU, and preventing the task that held the semaphore from releasing it. This can be solved by using a mutex, which supports priority inheritance, and we will cover that in the next video. That is it for today. You can download the project from the link in the description. Leave comments in case of any doubt. Keep watching and have a nice day.